Welcome to Brain Vision.
Hi everyone, so what we have is an insulated pipe that has steam flowing through it. At the inlet of the pipe, the pressure is 1200 kPa, the temperature is 250 degrees C, and the diameter of the pipe is 0.15 meters, and the steam is flowing through at 4 meters per second. At the outlet of the pipe, we know the pressure is 1000 kPa and the diameter is smaller at 0.1 meters. What we're asked to solve for is the mass flow rate and the velocity at the exit. So first thing we're going to do is write down our assumptions. So first we're going to assume that this is a steady state process and there's no changing with time. Next we're going to assume that changes in kinetic energy and changes in potential energy are negligible. And we're also going to assume that work and heat interactions are also negligible. So what we're going to do is actually define the system first, and we're going to define the system as the pipe. And when we do our energy balance, we see that the rate of change at which energy flows in minus the rate at which energy flows out is going to be equal to the rate of change of the energy of the system with respect to time. But since we know this is a steady state problem, this is going to be equal to 0. So therefore we have that the rate of energy coming in is equal to the rate of energy leaving. We can go ahead and expand upon these terms, and this is simply going to be m dot h1 is going to be equal to m dot h2. Therefore, m dots are equal, so h1 is equal to h2. So we know that the incoming enthalpy is the same as the exiting enthalpy. Next, what we're going to do is we're going to go ahead and look at the properties of the steam at the inlet and exit. So at the inlet, we know that the pressure is equal to 1200 kPa, and the temperature is equal to 250 degrees C. So with these two pieces of information, we know that the specific volume of steam at this state is 0.19241 cubic meter per kilogram. And we also know that the specific enthalpy is equal to 2,935.6 kilojoules per kilogram. Similarly, at state 2, we know that P2 is equal to 1000 kPa. But from the mass balance, we also know that H1 is equal to H2, which is equal to 2,935.6 kilojoules per kilogram. Therefore, with these two pieces of information, we can solve for the specific volume at 2, and that's equal to 0.23099 meters cubed per kilogram. So now we can go ahead and solve for the mass flow rate m dot. We know that m dot is defined as rho a v, and this is also the same as saying a times velocity over specific volume. Now we know that a at the inlet is going to be pi d1 squared over 4. That's just the area of the inlet, times velocity 1 all over specific volume 1. And after we plug in for these known values, we'll find that the m dot is equal to 0.3674 kilograms per second. So that's our m dot, that's our mass flow rate. Now we can use this to solve for the velocity at the exit. Now just rearranging the terms for mass flow rate, we can see that the velocity at 2 is given by m dot, specific volume at 2, all over the area at 2. Now plugging in for the terms that we know, we actually know all of these terms, we can see that this is going to be equal to 4 times m dot v2 all over pi d2 squared, and this gives us an exit velocity of 10.8 meters per second, and that's our final exit velocity.